Hello all and welcome back. In this section we will look a little more closely at the van der Waals equation of state in terms of the shape of its isotherms and in particular with respect to the critical point which marks the highest temperature at which the liquid and vapor can coexist with an interface or a boundary separating them. So let's go back to this drawing. Pressure versus molar volume. This is V molar equals little b. I'll try to sketch out the liquid vapor coexistence curve like so. And I'll draw just three isotherms for the van der Waals equation of state, which let's recall was RT divided by bracket V molar minus B minus A divided by the square of V molar. Okay. For a really low temperature, that's what the real gas would look like. The van der Waals gas does something like this, or the van der Waals equation of state isotherm is going to look something like this. At the critical temperature, what we have is instead something like this, and at a high enough temperature we see this. Okay, so what's happening? At this low temperature, at a temperature this low, we have this hill and valley, this pair of a pair of peaks and troughs, a peak and a trough. As the temperature rises, these get closer and closer, they get smaller. So I'll draw one more in here. So these curved lines with the trough and the peak, those are what we get when we plot out isotherms from the van der Waals equation of state, again for a given fixed value, chosen values for A and B, different temperatures for each of these lines. Okay. As the temperature rises, as we did this, the width of this trough and peak get narrower and narrower, they get closer to each other until at this point, that isotherm, that line corresponds to what we call the critical temperature. How do we know it's the line at the critical temperature? What distinguishes it? What's different at this temperature for this line from either this one or this one is what's happened. That's the temperature at which this pair of points just merge, where the trough and the peak, the hill and the valley, they get closer and closer until they just merge, just line up on top of each other, and they also line up with the point where the slope on this curve is changing sign. So this point here at the top of the curve, that's a point at which uniquely the slope dP over dV molar at fixed temperature is 0, and also I'll explain the notation in a moment. d2p dV molar 2, second derivative of pressure on the molar volume, are both 0. Okay. dP over dV molar. We know that dy over dx is the slope. Here the y variable is pressure, the x variable is molar volume. So d of p with respect to d of v molar, that's the slope of one of these curves. That's just the slope. At this point, what we are saying, the slope of the curve is 0. Okay, what's about this vertical business with a t at the bottom? All that this says is we are taking the derivative of the pressure on the molar volume, holding the temperature fixed. So the vertical line with t at the bottom, that's simply a language. Mathematics is just a language, a way for a means of communication. That says we are differentiating this, treating temperature as a constant. And why do we keep temperature constant? Each of these lines is an isotherm. Isotherm, fixed temperature. So on each of these lines the temperature is fixed, and at this point the slope is 0. Well, that's not such a big deal because if you look at these, the slope 0 here, it's 0 here, it's 0 at this and this trough, it's 0 at this peak. There's a whole bunch of points where it's 0. But also simultaneously, the second derivative of pressure on molar volume also at fixed temperature is 0. Why is that? Why does that happen? Physically speaking, that happens because that's the point, the unique point, the only point on this diagram where this trough and this peak have just merged. So we have this minimum, this maximum, this point where the second derivative is 0, they've all merged. They all merged together at that point. So simultaneously the slope is 0 and the slope of the slope is also 0 at the critical point. Two derivatives differentiating the pressure 2 times on the molar volume, holding again the temperature fixed. Both of these conditions are true simultaneously at the critical point. And that is what is unique about it. And by the way, this that we are discussing, this piece of the discussion is universally true regardless what equation of state you are using. The only thing that is van der Waals specific about this diagram is I said V molar equals little b was where the pressure went to infinity. That reflects the fact we are using the van der Waals equation of state. Other than that, this business that the slope of the pressure on molar volume at fixed temperature is 0, as well as the second derivative of the pressure on molar volume at fixed temperature are 0 simultaneously, that defines the critical point, that is a universal thing. Okay. With that said, let's look at what we can do with these relations, where this takes us for the van der Waals equation of state. Oh, and before I do that, I should point out for those of you, for those who have taken several extra classes in calculus 1, 2, 3, 4, 5, 6, 7, I don't know how many calculus classes there are. This notation d of p of dv molar, vertical line, t is t at the bottom saying at fixed temperature, this is called a partial derivative. This is also a partial derivative. It's the partial second derivative of pressure on molar volume. I am deliberately not using the language of partial derivatives, and we will do very little with it, as little as we can get away with, because I am well aware that most people, in fact the vast majority of people in the class, have not taken calculus 3 and are not familiar with partial derivatives, and that is not required for this class. So we are not going to make heavy use of this, but when it shows up once in a while, it does not hurt to make people familiar with the language, because this is how we learn different mathematical terms also. And just because something has a fearsome name like partial derivative does not mean we should be afraid of it. All it is it says we are differentiating one quantity on another, holding something else fixed while so doing. Okay. So let's see what we can say using the van der Waals equation of state for this. What I'm going to do now is I'm going to try work through what's on page 9 in the notes. This is perhaps one of the more mathematically heavy parts of the class, and I do not want people to be dismayed by the fact we are running into some little bit dry and a little bit heavy mathematical things early on. In terms of what we discuss in the class and what I expect people to be able to do in an exam context, there is a wide difference. I want to go through this derivation a little bit carefully so people see there is nothing magical or nothing super top secret or mysterious that is happening, so people can see all the steps, even though I don't expect people to be able to do those in real time in a timed exam or what have you. But I just like people to have the complete story. So at the critical point, the isotherm, line of constant temperature, shows a point of inflection. Point of inflection is simply another way of saying second derivative is 0 with 0 slope, first derivative is 0, and it turns out that allows us to determine the critical pressure, temperature and molar volume in terms of the A and the B parameters. Or in other words, if we know P critical, T critical and V molar critical from experiment, we can then determine the little a and the little b quantities from those data. Okay, we have P critical, T critical, V molar critical, 3 unknowns, one for the pressure, one the temperature, one for the V molar. There are 3 unknown quantities. If we want to determine 3 unknown quantities in terms of little a and little b and the gas constant R, we are going to need 3 equations. In general, if you have 2 unknowns, you need 2 equations. If there are 10 unknowns, there are needed 10 equations. So for 3 unknowns, we require 3 equations. So what are our 3 equations for 3 unknowns? The first is very simple. We know that the critical pressure and critical temperature and critical molar volume are all, they have to satisfy our equation of state. So we have this van der Waals equation of state here, where what I've done is I've taken the van der Waals equation of state and simply substituted P critical, T critical, V molar critical as relevant because this is the equation of state we are working with. Okay, so let's write the equation of state down again. Pressure RT divided by V molar minus B minus A divided by V molar squared. The second equation, so this is equation number 1, I will call that equation number 1. The second equation comes from enforcing that the slope dP over dV molar fixed temperature has to be 0. So let's calculate for ourselves the derivative. Let's get some practice in this, in how we calculate this. So the pressure is this, dP over dV molar at fixed temperature. Temperature is fixed, so nothing happens to the temperature. We have V molar minus B in the denominator. We get minus V molar minus B squared when you differentiate this. What I did here is d over dV molar of 1 divided by V molar minus B is minus 1 over V molar minus B squared. That's what I did here. That's what happened. That's what gives us this. How about this? Plus twice A over V molar cubed, and that equals 0. What I did there is d over dV molar of 1 over V molar squared is minus 2 divided by V molar cubed. Just the rule of differentiation. So we get that is 0, and that is 0 at the critical temperature and the critical molar volume. And that is equation number 2. We have now 2 equations in 3 variables. We need a third, and the third is obtained by taking 2 derivatives on the molar volume of pressure on the molar volume at fixed temperature, and that is differentiate this one more time on the molar volume. What do we get? We are keeping the temperature fixed, the gas constant is a constant. We get plus twice R T V molar minus B now to the power 3 minus 6 A over V molar cubed. That is equal to 0 when we put in T critical and V molar critical. Now we have ourselves 3 equations in 3 variables. And if you look closely, these are the same, or should be the same, if I did things correctly, as the 3 equations on this page. What I called equations A, B, and C are what we had there. So we plug in T critical, V molar critical in each of these, equation A, equation B, equation C. We have now 3 equations in 3 unknowns that are the T critical, V molar critical, and the P critical. The pressure appears in this equation. So we solve the 3 equations in 3 unknowns. This is an exercise only for those who are really who enjoy going through lots of algebra. I do not expect everybody to do this. The simple thing to do is to take the results and plug them back in here and make sure that they satisfy the 3 equations. But solving those, we find that V molar critical equals 3 times B, T critical equals 8 multiplying A divided by 27R multiplying little b, and the P critical is A divided by 27B squared. That's a 7. So you can take these and plug them back, plug in this for B critical, for V molar critical, this for T critical, this for P critical into this set of equations, and you will find all of them are satisfied, thereby verifying that we have solved these equations simultaneously, 3 simultaneous equations in 3 variables correctly. This is useful because it tells us now that if we look at, say, a given gas, say nitrogen, and experimentally we know the critical molar volume, we know the critical temperature, if we know that from a measurement, then we can use that to calculate little a and little b for that gas. Or if we know the critical pressure and critical temperature, we can calculate little a and little b, put them in a table, store them in our toolbox, and if we want to know how nitrogen behaves under a completely different set of circumstances, we can use that pair of values for little a and little b for the new temperature and pressure to calculate, say, the molar volume, and so on and so forth. This is interesting. It tells us that the critical molar volume is closely related to the close-packed volume, the smallest volume into which a mole of particles can be compressed. So now, having gone through this, we may be ready now to do an example. And let's move on to consider a problem. And the problem I would like to move on to is let me look for a good one. Yes. Problem set number 1, let's say problem number 5. And I will state what the problem is for people who may not be able to immediately see, to read this thing from the problem set. This is for methane, CH4, we are told P critical is 45.6 atmospheres. We are told V molar critical, the critical value for the molar volume is 98.7 centimeter cube per mole, and T critical we are told is 190.6 Kelvin. This problem has 2 parts. The first part is to calculate the van der Waals parameters for methane, or in other words A and B, for the van der Waals equation of state for methane, and the second part is to calculate the approximate radius. I'll call this little r for radius r for a methane molecule. Let's look at the first part first. Okay, to tackle the first part, we need to go back and look at these equations. P critical, V molar critical, T critical, we are given numbers for them, and it says to calculate A and B. What do we know? What we know, and people do not need to memorize this does not need to be memorized. This information, if needed, will be provided. What I'm trying to convey to people is how to use equations like these for the critical molar volume, pressure and temperature with information to get other information. Here we are given critical pressure, temperature and V molar. These equations tell us if we are given these, we can calculate A and B. So let's see. We have 3 equations. I want us to keep my life simple. I will simply use the fact we are told V molar critical equals 3 times B for the van der Waals equation of state. If we had a completely different equation of states, let's say we were working with the Peng-Robinson equation of state, which is fashionable these days, and yes, which equation of state engineers work with, the equations of state named after different famous scientists and engineers, these go into and out of fashion, and then things can come into and out of style because scientists are not immune to considerations of what goes in and out of vogue any more than anybody else. Anyway, but in the van der Waals equation of state we have this. Here we are given information for this. So what we can say is if we want to calculate B, that is 1/3 of V molar critical, and that is 1/3 multiplying 98.7 centimeter cube per mole, which is 32.9 centimeter cube per mole. But let's say I like using metric SI units, I don't like the centimeter cube, I want to convert this to cubic meters. This is the same as 32.9 multiplying 10 raised to the minus 6 cubic meters per mole. Okay? Why so? Because 1 cubic meter is 10 raised to the power 6 cubic centimeters. So many cubic centimeters is this 10 to the negative 6 cubic meters per mole. Okay, we got B. How about A? Well, I go back to here and I see T critical is expressed in terms of A, B and capital R. I already know B. We have a value for little b for methane. We can plug in for B into this equation and calculate little a. Let's see how that goes. T critical is 8 multiplying A over 27 capital R multiplying B, or little a, the quantity we do not yet know and have to discover, is 27 R multiplying B multiplying T critical, just multiplying by 27 R times B, divide by 8. Okay, we have a value for little b. Therefore, A is going to have the value 27 multiplying for R, let's say 8.314 units joules per Kelvin per mole for R, little b 32.9 multiplying 10 raised to the power minus 6 cubic meters per mole. Temperature, critical temperature was 190.6 Kelvin, 190.6 in Kelvin divided by 8. And let's see what that gives us. 27 multiplied by 8.314 . That gives me 1.408, but in what units? Let's look at the units. The units are joules per Kelvin per mole from here, cubic meters per mole here, and Kelvin. So let's see. The Kelvins cancel out. This is in joule meter cube mole, that's an O, mole to the power minus 2. The reason I'm ending up with A in slightly different units, not in the liter atmosphere type units, is because I'm keeping with metric units. I'm keeping the energy in joules and the volume in cubic meters, so that's why A ends up in these units. Okay, so that's A, that's little b. We have solved the first part of this problem. The second part of the problem asks, what's the radius for a methane molecule? How do we estimate this? Think about it this way. What information do we have? Just A and little b. Little b is 32.9 10 to the negative 6 cubic meters per mole. What is little b physically? Physically, little b represents the smallest volume you can squish 1 mole of molecules into. So what's that going to look like? When you squish the molecules really, really close on top of each other, basically they are forming a close packed array like so, and you can't push them any closer. So the closest they can get, I'm drawing a very cartoonish simple figure here, is when each molecule, if you pretend methane is a sphere, CH4 approximately spherical, pretend it's like a sphere, and it sort of is if you don't look at it too closely. Pretend it's a sphere of radius r. The closest you can get to molecules is when their centers are apart by a distance equal to the diameter, twice times r. And this is an estimate. This is not going to give you an exact or an accurate answer. It's just to see what the order of magnitude is for the size of a molecule. So when they are really touching each other, you can think of it as each molecule, each spherical molecule is inhabiting a box, and these boxes are just touching each other, where the side of the box is equal in length to the diameter of the molecule. So we can ask, what's the volume of each of these boxes when you have squished an Avogadro number of molecules down into this little b volume? Minimum volume per molecule equals little b divided by the Avogadro number. I'm calling this n sub AV for the Avogadro number. Remember, the Avogadro number is the number of particles, molecules or atoms in 1 mole of a substance. So that is 32.9 10 raised to the negative 6 cubic meters per mole, divided by the Avogadro number is 6.022 10 to the power 23 molecules per mole. And that gives us 5.46 multiplying 10 raised to the power negative 29 cubic meters per molecule. So that's the volume of each of these little cells into which one molecule inhabits. Okay. If we have a cell, a cubical cell, whose side is of length twice the radius of the molecule, the volume of the cell is 2r to the power 3, right? 2r, 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 that's the volume of the cube, 8 multiplying r cubed. So 8 multiplying r cubed becomes 5.46 10 to the negative 29 cubic meters per molecule. Or r is, we divide this by 8 and we take the cube root. Cube root of 5.46 10 to the negative 29 cubic meters divided by 8, and that is going to be what? I get about 1.9 multiplying 10 raised to the negative 10 meters from this. That's the value of r. So I divide by 8, take the cube root. That's an estimate for the radius of a methane molecule. Now, there have been many approximations made here, and let me check this number. Let me check this number. Yes, this seems correct. So this is an estimate for the radius of the molecule. which is built on a lot of approximations. First of all, the first approximation is we are treating the van der Waals, we are applying the van der Waals equation of state, which itself is an approximation. Then we are making the approximation that the methane molecule is approximately spherical. Well, methane is a carbon atom tetrahedral structure, 3 hydrogens, so it's roughly approximately spherical in shape. And then we use the value of little b, pretending that the molecules are in cubical cells squished together, so that the distance between the centers of individual molecules is equal to the diameter, and that becomes the diameter of a molecule, and that we equate to the length of the side of a cell. We take the third power of that, 8r cubed, and from that we estimate the radius of a molecule. Now, this is not going to be accurate, but the impressive thing is that it is even in the correct power of 10. It's within a factor of 10 of the correct estimate, and this is based on a sequence of very crude approximations where, for example, we have neglected or not really carefully accounted for the empty spaces between molecules. Because think about it, when you have a jar of marbles and you squish marbles close together, not all the spaces is taken up by the marbles. There are some empty spaces and voids left between them. We have been a little careless in how we handle that, but just said it's a cubical array of boxes, each houses exactly one molecule. And even this very crude estimate, where we are starting with strictly macroscopic data, temperature in Kelvin, volumes in cubic centimeters per mole, pressure in atmospheres or pascals, with strictly macroscopic data, and the only microscopic data that makes reference to the existence of atoms and molecules is the Avogadro's number, we are able to obtain an estimate for the size of a molecule that is within a factor of 2, I would say, of the correct answer for this molecule. This is very interesting and very remarkable that we can obtain such a microscopic level of information starting from purely macro level measurements. So today we have seen an example of the use of the van der Waals equation of state in conjunction with critical pressure, molar volume and temperature data. We have looked at how we can use the van der Waals equation of state in conjunction with the fact that the critical point for a material is a point at which the first and second derivatives of the pressure with respect to molar volume both simultaneously vanish, to obtain expressions for the little a and the little b parameters in terms of the critical pressure, volume and temperature. If we were working with another equation of state, say not to pick on it, but the Berthollet equation of state, we would be doing the same thing. It's just the equation would be different and the structure would be different, but that would have its own A and B parameters for, say, nitrogen or oxygen. We would go through a very similar calculation with that different equation of state and obtain little a and little b by setting the slope and the slope of the slope of the second derivative to 0 simultaneously and using the equation of state to obtain a and b there. The structure of this argument we have gone through today is common to whichever equation of state we look at, and that is something that unifies these different applications. That said, next day what I plan to do is work through another example or two using this van der Waals equation of state, and it will be time to move on to our next subject, the kinetic theory of gases. Thank you very much, and that is all for this section. We'll see you next time. Thank you.